let's look at an example with a mass hanging from a spring. So let's say we have a 20-gram mass that stretches the spring 4 centimeters. Let's figure out what the frequency that the mass will oscillate at is, and also let's figure out the motion of the mass, assuming that we pull it down an additional 5 centimeters and then let go. So in general, we know that we're going to get the differential equation m times y double prime plus k times y equals 0. And we know the mass. We don't know k yet. But once we find it, we know that the angular speed of this situation will be the square root of k over m. And also, we will know that the general behavior of this kind of system is y equals some constant times sine omega t plus some constant cosine omega t. And it's the initial conditions that determine these constants. So all we need to do really is figure out k. And k tells you how strong the spring is. And if you look at this description, what tells us how strong this spring is the fact that a 20-gram mass, I guess we're assuming we're near the surface of the Earth, gravity stretches the spring, gravity acting on the mass stretches the spring 4 centimeters. So that's what we're going to have to use to figure out the spring constant for this spring. Now in general, the spring constant has units of force divided by distance, because it tells you how hard the spring pulls if you stretch it a certain distance. But since we're going to have gravity in the mix, right? Usually the acceleration we do to gravity, the value we use is 9.8 meters per second squared. And since we're using meters here, we need to convert this distance to meters. While we're at it, maybe just to get units we're used to, we should also convert this mass to kilograms. So this is 0.02 kilograms, or 1 over 50 kilograms, and 4 centimeters is 0.04 meters, and that's 1/25 of a meter, I guess, if I have my arithmetic right. So now that we have these values in units that we want, let's figure out the force. Now the force that the spring exerts on the mass. So this is an equilibrium force, right? The force in general, it depends on how long you stretch the spring. So it's minus k, which we don't know yet, times times the distance. So Hooke's law says it's minus k times the distance, which is 1 over 25 meters. But the force that's doing that stretching, so minus 1 over 25k, the force that's doing that stretching is gravity, and gravity is acting downwards, so we need a minus sign, and the force due to gravity is mass times g, so mass is 1 over 50, and g is 9.8 meters per second squared. So now we can solve for k, so multiply both sides by minus 25. We get k is 1/2 times 9.8. So that's going to be 4.9, I guess. And this is going to be in newtons per meter, right? If we hadn't used grams, if we had used grams instead of kilograms, this unit wouldn't be in newtons per meter. The force unit would be something else, because a newton is like a kilogram meter per second squared, something like that. So the mass unit is hiding inside of newtons here. So to use newtons, we have to use kilograms. All right, now that we know k, we can go ahead and figure out our angular speed. Angular speed is the square root of k, which is 4.9 over m, which is 1 over 25. Because we're using consistent units, we can neglect the units as we do this calculation. It will come out to be in radians per second, which is what the units for omega are. So let's do this calculation. So 4.9 divided by, or times 25, I guess, square root of that. So 11.1, and this is radians per second. Okay, the period is 2 pi over omega. So I guess, you know, it didn't explicitly ask for the period, but that's 2 pi over omega. So let's do 2 times pi divided by 11.1. This is 0.566, and that's going to be in seconds. And the frequency is just 1 over the period. So the reciprocal of this, and that's 1.77, it looks like, rounding it off a bit. And this is in units of per second, otherwise known as hertz. So cycles per second. So 1.77 cycles per second is the frequency that this mass will oscillate at. Okay, now for part B. If the mass is pulled down an additional 5 centimeters, so additional, that is beyond the stretching happening due to gravity, and released, describe its motion. So remember this differential equation that we wrote down up here. This is the differential equation, assuming that y equals 0 is the equilibrium position. So this initial condition of an additional 5 centimeters means that y at 0 is minus 5, because we're stretching it down 5 centimeters below the initial, below the equilibrium position. And actually it shouldn't be 5, that's 5 centimeters, but remember we're measuring distances in meters, so it should be minus 0.05. Okay, and since we're releasing it, right, we aren't throwing it upwards or downwards, we're just letting go, that means the initial velocity is 0. Okay, so we can use these two initial conditions. Since y of 0 is minus 0.05 meters, if we plug y of 0 into our general solution, we get c1 sine of, I'm going to write sine of 0 plus c2 cosine of 0. And so c2 is minus 0.05. All right, to use our initial condition for velocity, we need y prime. Y prime is omega times c1 cosine omega t minus omega times c2 sine omega t. We do know omega, but I'm just too lazy to write it down. So now we can use our initial condition. 0 is y prime of 0, so now plug 0 into our expression for y prime, and we get omega times c1, and so c1 is 0. And so now we have our solution to this initial value problem. Y is minus 0.05 times cosine of omega, which was 11.1 t. And there we go.